Yeah. Okay, hi everyone. I'm Shiqi, and today I'm going to present you our paper, Formal Security Analysis of Neural Networks using Symbolic Intervals. This paper is co-authored with Ke-Xin Pei, Justin Whitehouse, Junfen Yang, and Suman Jana, all from Columbia University. In this work, we mainly focus on providing formal guarantee on neural network efficiently by leveraging interval analysis. Okay, first of all, let me introduce some background of machine learning systems. These systems are gradually deployed in many security critical domains, like autonomous vehicles by Tesla and Google. Also, unmanned aircraft systems are going to be installed by US Navy. We can see these systems have huge potential benefits. However, we are extremely concerned about their safety and security. In recent years, there are 3 different fatal crashes caused by the mistakes of self-driving vehicles. So actually, they are not so robust or reliable enough to be applied in these critical domains. Okay, so what's the problem? One of the potential reasons that might cause these accidents are adversarial examples. It means that with minor perturbation on valid input, the neural network will misclassify it with high confidence. For example, if we add an imperceptible adversarial noise on a school bus image, then the neural network will regard it as an ostrich, and this will cause a severe accident. In the previous papers, adversarial example has been proved as an inherent weakness of neural network. Currently, there's no scalable techniques can be provided to prove the non-existence of adversarial examples. So to avoid their existence and avoid these tragedies, formal analysis on neural networks is urgently needed. Okay, today we'll first talk about what kind of safety properties that we want to verify with, and what exactly is formal analysis, and why formal analysis on neural network is very difficult. After that, we'll introduce our own method, removal, by leveraging interval analysis, and we will illustrate it has strong ability to locate the counterexample and efficiently verify certain safety properties by showing experimental results. And finally, we'll summarize a little bit and provide several interesting future works. Okay, first of all, what safety properties? Consider a neural network, and given the input range. For MNIST, it can be like bounded by p-norm. And in general, it can be any customized range x and y. And given the input range, the neural network will provide us the output range f. We want to check whether the output f always satisfies the property p. If it is, then the property has successfully been verified. Otherwise, we can locate counterexample and prove it unsafe. However, it's very hard to provide the analysis on the output. We'll explain later. And to handle such problem, formal verification system has been proposed. They will take in the neural network and the safety property and verify whether the property are always satisfied, which is safe, or locate counterexample, which is unsafe. Okay, here we explain why provide the formal analysis on the output of the neural network is very difficult. Consider a neural network without any activation function, then the output is only a combination of linear functions, so that itself is linear, so that it's very easy for us to analyze the output range. However, with the ReLU, which has 2 linear pieces, and there's one nonlinear turning point at 0, then the ReLU-based neural network's outputs are determined by the combination of ReLU nodes, ReLU pieces, and these linear pieces exponentially increase as neural network gets larger. For example, here there's one hidden layer and d hidden nodes in the hidden layers. Then that will be due to second linear pieces, like the output function here. Okay, if there are 2 hidden layers due to the 4th linear pieces, and layers, that will be due to the nth linear pieces, which is very difficult for us to accurately and efficiently analyze the output range, and it's very expensive to track all linear pieces. So there are 2 existing approaches that have been provided. The first one is to extend the current linear solver, It can first over-approximate the upper range and then lazily add the ReLU backs. Okay, it will first check the satisfiability with customized SMD solver at Simplex used by ReLUplex. And if it is unsatisfiable, then the property is truly unsafe. Otherwise, they will add the ReLU back and check again. However, such solver-based verification system has a limitation that the solver will incur high overhead, and it will usually take hours or days for simple properties. And because of such limitation, they cannot scale to large network. And the second method is to use certain method to relax or over-approximate the output function, like abstract domain, or use convex relaxation and solve the problem as a convex optimization problem. And these systems are very efficient, but they will suffer from high false positive rates when the neural network gets larger, and they can't efficiently find or locate the counterexample due to the false positives. Okay, so to handle such problem, we propose removal, which leverage interval analysis. So why interval analysis? We notice it is a natural fit for neural network verification problem. First, it is very fast, and it can always approximate the upper range, over-approximate, because it's the functions in the neural network only has linear functions and ReLU functions that are fixed and simple, so that interval can easily over-approximate the output function and give the soundness estimation of the output. And most importantly, interval analysis allows us to iteratively refine the output range by bisect and union the output range. With certain step of refinement, it can approach any functions like this one. So here, we give a simple example to show how we can apply interval analysis to verify certain safety properties. Given a neural network, which has the input as distance x and the approach angle y, it will output the theory angle f, and we want to check whether output is always less than 20. Here, we will first propagate the input interval to the hidden node A according to the weights, and we get a range as 11 to 27. After going through the ReLU, it keeps the same because it's always larger than 0. The same process goes for B and F, and finally, we get a range as the output as 0 to 22. Now, the estimation shows there might be violations for this safety property. But we notice they are only false positives because of dependency error. So what's dependency error? Consider another simple example. Consider x is from -1 to 1, and what's the range of x minus x? The interval analysis tells us it's -2 to 2. But obviously, we know the output should be 0 to 0. So what's the problem? Because when we propagate the interval through the neural network, certain dependencies have been ignored. So to handle such problem, symbolic interval analysis has been proposed by us. It means that we keep the symbolic linear upper and lower bound equations for each ReLU in terms of inputs. And we can easily track the dependency of the output by keeping such symbolic intervals. So consider for the same example, we propagate x and y to the hidden node A and get the symbolic interval as 2x plus 3y to 2x plus 3y. And the same for B and F. Finally, we get the range as 6 to 16 by tracking the input dependencies. Now we have verified that the property is safe because F is always less than 20. However, we notice that this method is not always perfect, because at certain ReLU nodes, nonlinearity truly occurs, so that the symbolic interval has to be concretized with its concrete upper and lower bound. And in the paper, we have shown that the overestimation error of the output is only introduced during these concretizations. And when the neural network gets larger, then this method will suffer from high false positive rates. Okay, so here consider for the same safety property, but with another neural network with slightly changed weight of hidden node B. Then here, the symbolic interval of B cannot be kept because the nonlinearity truly occurs. So that we have to concretize it as 0 to 16. And we propagate to the output and get range as -5 to 27. So there's no guarantee can be given for this property anymore. So to handle these kind of safety properties, we propose another method called iterated interval refinement. We first bisect the input range and union the corresponding output range, and we can do such refinement iteratively until the property has been verified. Okay, here we first split y to 1 to 3 and 3 to 5, and we propagate 1 to 3 to the output as 0 to 21. And we propagate 3 to 5 as -4 to 18, and we union these two corresponding output range and get the final range as -4 to 21. We can see now the estimation has been tightened. Okay, to further verify this safety property, we do another step of split on node y and union all of the 4 corresponding output range and get the bound as 3 to 19. Okay, now we have verified this property is always safe because f is always less than 20. So let's take a deep look at this simple example. First, without any bisection, there's no guarantee can be given. Then we split on y. There's no need to further split on y for this case, for the left subtree, because it has been successfully verified. So we split on y for the right subtree, and we have successfully verified both of its children, and we union all of the leaves, and finally we propagate, we union the output range, and finally verified property safe. Okay, as we can see, such bisection tree is highly unevenly distributed. There's no need to split for safe subtrees, and we can flexibly refine the output range based on the property. And this process allows us to iteratively narrow down the adversarial range and easily locate the counterexamples. And also, each subtree is independent, so that the whole process is highly parallelizable. Okay, there's another problem, that which feature should we split first? Consider for the same example, we first split on y, but then split on x. With 2 steps of refinement, there's no guarantee can be given for this property. Now we can see the sequence of split actually matters. So we use smear function as a heuristic to estimate the feature's influence, and we always split the most influential feature to achieve the best performance. Okay, there are some other optimizations used in removal. First is monotonicity. We find the input range where output is monotonous, then we can simplify the whole range as its concrete upper and lower bounds. Also, to improve the performance of parallelization, we use certain heuristics to estimate the workload of each thread and dynamically assign the workload to idle threads to increase the performance. And to keep the soundness of floating point numbers, we do outward rounding. And we notice there are 2 false positives reported by Reluplex caused by such problem. Okay. Now we have provided all of our methods and optimizations, and we will show our results on different datasets. First, we evaluate removal on XSU model, which is an album collision avoidance system, and it has 5 inputs: distance, approaching angle, speeds, and it will output 5 stereo angles, and it has 16 layers, each 15 nodes in each layer. And here we give a simple example to show what kind of safety property on XSU could be. Given the input range like this one, we want to verify whether the output of weak right is always the minimum. After symbolic interval analysis and iterative refinement, removal will return the output range of weak right as 0 to 3. And you will find that it is always less than the other outputs, so that it can successfully verify this property safe. Similarly, we evaluate removal on 15 different safety properties on XSU, 10 from original ReluPlex paper, and 5 additional new safety properties. And overall, we can see removal is over 200 times faster than ReluPlex on average. Okay, and also on XSU model. Okay. We compare with Kalini-Wagner attacks, which is currently state-of-the-art attack, gradient-based attack, and it can efficiently find counterexamples, but there's no formal guarantee can be given. And we test on 40 unsafe XSU properties, and as results have shown, removal can find 35% more counterexamples compared to current state-of-the-art attacks. And finally, we evaluate removal on MNIST network, which has achieved decent accuracy. And we test on 1,000 random images, each bounded by L infinite norm. If the range is less than 3, then removal is able to verify most of the safe images. However, if the range goes larger, then removal will suffer from high false positive rates and usually times out during the iterative refinement. Okay, finally, we'll summarize a little bit. Symbolic interval analysis is a good tool for checking the neural network properties, and it can efficiently and soundly approximate the operand, and it can further refine the operand by bisecting and union the operand. Also, removal is on average 200 times faster than currently state-of-the-art solver-based verification system ReluPlex, and it can flexibly refine the operand based on the desired properties, and it can efficiently find the counterexamples compared to the other relaxation methods. And there are several new exciting directions. First of all, we can further support other activation functions with removal in the future, and such methods can be incorporated with robust training to improve the neural network robustness. Also, we can apply SMD solver to further improve the performance and the efficiency of iterative refinement and to further improve the performance. Okay, thank you. That's all. And our code of removal has been published at GitHub. So I'd like to take any questions.
Thank you. So if you have any questions, please come to the microphone. Let me start by asking a question. So these sort of interval-based safety properties. I mean, you showed how you evaluated some of them from this prior work, the ReluPlex. But I was wondering, how do you come up with such safety properties that make sense, right? So, like, how do you come up with a safety property that would have prevented the Uber crash, for example?
Okay. So currently, safety properties can be defined by different methods, but most of them has been defined as L infinite norm in previous work. So we use the same things as the previous work. Also, we propose other methods like customize the range used in XSU model, but there are a ton of other types of safety property can be provided, but we want to show that interval analysis can verify certain types of attacks or safety properties bounded by interval or infinite norm or customize the range. So that's the hope in this paper.
So one more question, actually. So I'm trying to understand where these types of properties would be applicable. So do you think that outside of the image classification domain, so let's say that we had a malware detector that's based on machine learning.
A malware?
A malware detector.
Okay.
Right? Would you be able to define a set of safety properties that are interval-based like this?
Yeah. Usually, like for PDF malware detection, the PDF can be passed as 0 to 1 for each feature, and it might have 10,000 features each from 0 to 1. We can specify kind of very sensitive features as 0 to 1 as the range. We want to show whether after we changing these sensitive features, then the output will be be changed from like a misclassified from benign to like malware. Yeah, that's the kind of safety process that you care about, but we can bound it by 0 to 1 for that feature and propagate through such process, and we can verify this kind of safety properties.
Okay, so one more question, and maybe the next speaker can set up.
Hello, this is Sang Yeonong, and I'm from University of Maryland. Thanks for the interesting talk. So I have a simple question. So how do you heuristically select some of the important features in the MNIST example, for example? So can you provide a little bit more the process of selecting the important features?
Okay. Previously, we have talked like about smear function.
Answer the question while the next speaker sets up, right?
Okay, sure.
We need to move on. Yeah, just answer the question, but the next.
We use smear function. Okay, thanks. We use smear function to estimate the most important features. Smear function is basically determined by two different things. One of these is that the width of the input features, and the second one is the absolute gradient value of this feature. We combine these two things as the most important things that we want to consider as the split features, so that if the smear value, which is a combination of these two factors, is large, then we say it is very important for split, and we will split it first.
Okay, thank you.
Thank you for the question.
Again.